So let me start from this first part, so kinetic theory of the gases. So let us consider particles of gas as in this picture. This can be gas or any particles of the plasma. Let's assume this gas has n particles, and this n is very big. And so we want to study the time evolution of these particles. So we want to study the evolution of the gas as time goes to infinity. So there are different ways to study these particles. One way is just using this classical mechanics. So we consider this every particle as a dot, and we can define its position. For every particle, we define its position by xi and its velocity by vi. So I here from 1 to n because we have n particles, and t is time. And if we just follow the classical mechanics, we can write following ordinary differential equations. So it's according to Newton's second law, the time derivative of the position equal to the velocity, and time derivative of the velocity is acceleration, and mass times acceleration equal to the force. So here mi is the mass, and fi is the force. So this force can depend on the position and velocities of the other particles. For example, this force can be gravitational, or if the particles are charged, we can also take into account the electrostatical forces. So we get this OD, and one can try to use this OD to study the evolution of the particles. But we will get very serious problems to study these ODs, because a typical gas has a very large number of particles, not something like this number, and solving this number of coupled differential equations is extremely difficult, because we have to write this OD for every particle, and we have n particles, and its number is very big. Also, before thinking about solving this OD, we also need to know the initial conditions, at time t. But since we have lots of particles, and in general, practically, it is not possible to know the position of each individual particle. Therefore, it is not, in practice, it is not possible to solve this ordinary differential equation. So also, experiment shows that these trajectories of the particles are very complicated. You can just imagine like billiard balls. If you touch one billiard ball and they collide each other, and their trajectories are very complicated, and so it's the trajectories are not stable. However, we can study these particles different way. Well, in experiment, we can check that some statistical properties of a gas, for example, its density, pressure, and temperatures are generally stable. They don't change rapidly. And also these quantities are independent of the precise initial conditions of the initial data. Hence, we may not be able to study each individual particle, but we can study statistical point of view. So we can study the statistical properties of the gas. And so there is a branch of statistical physics. It's called kinetic theory of gases. This field studies gases or any system with many particles in a statistical point of view. In this theory, we forget about each individual particle, but we are interested in the statistical properties. And in this field, the main object is a distribution function, f. It's a function of t. T is a time, x position, and v. This function means the probability of having a particle at time t with position x and velocity v. If we know this, if we know the evolution of this distribution function, we can get information about the statistical properties of the gas. Hence, we want to know what type equations this distribution function satisfies. This has been done by famous physicists Maxwell and Boltzmann. They assume that if gas is dilute and if we assume that collisions between particles are elastic means the particles collide like billiard balls. And if we neglect collisions of the three or more particles at the same time, so we can assume only two particles can collide at the same time, and we neglect the collisions of the three and more particles. Under these assumptions, at the end of 19th century, Maxwell and Boltzmann wrote this differential equation, partial differential equation. And nowadays, this is called the Boltzmann equation. So on the left-hand side of this equation, we have just the transport equation, just first-order derivatives. But on the right-hand side, we have an operator Q. Q is a nonlinear integral operator. Here, this S2 denotes the unit sphere in R3. B is a given non-negative function. This function often has singularities depending on the gas and the modeling. But in this talk, I don't want to give the precise form of this B, but we have such a kernel here. And also in this operator, you can see we have V star, and V prime and V star prime. They are connected with this expression. And here, the sigma varies in this unit sphere. So after integrating this operator with respect to this sigma and V star, we get some function depending on t, x, and v. So this is a Boltzmann equation. It was obtained by the Maxwell and Boltzmann, and nowadays people call it the Boltzmann equation. This equation is very fundamental and very old. However, this equation is very hard to study because this nonlinearity, and since this function b has singularity, there are so many open questions. For example, there is no good existence results for this. So after this introduction of this Boltzmann equation, different versions of this equations has been suggested depending on the model and depending on the situation. I just want to give some examples. So many kinetic equations has this form. So so in this Boltzmann equation, we have initial data. Initial data is since we assume f is a distribution function, this f0 is also non-negative, and we assume it's in L1. So kinetic equations has this form, and we can change this operator Q, and depending on this Q, we call this equation with different names. For example, if Q given in this divergence form, we call this equation kinetic Fokker-Planck equation. Another model was given by Landau. If Q given by this integral operator, here we have a divergence with respect to V, and A is some function given by this form, which can have a singularity depending on this gamma. And yes, we have this gradient of V. And this equation was obtained by Landau to model Coulomb interaction of the particles. And another model is suggested by Bhatnagar, Gross, and Krog. In this case, this collision operator has this form. Here, rho is integral of the f with respect to v, and u is defined by this integral. So if we know the rho, we can define u by using this formula. So we integrate this f by multiplying with respect to v. There is also another function t. T is defined by this integral. And so this is a highly nonlinear model, and it's called, in short, BGK equation. And there are some examples of the kinetic equations. All of these equations are obtained following the classical mechanics. However, one can follow the relativistic mechanics, and one can write a relativistic version of these equations. Also, one can also follow the quantum mechanics, and we can get the quantum version of these equations. And nowadays, if you have two different type of particles, we can also consider the mixture of the two gases, and then we have to consider the system of these equations. And nowadays, these equations use it to different fields to model many things in our life. For example, these equations are nowadays using in mathematical biology. And these equations has some properties coming from physics. For example, these equations, which I told you before, for example, this Boltzmann, Landau, and BGK equations, all of them satisfy these following properties. If we assume there exists a very nice smooth solution, we can integrate this equation with respect to x and v and get the time derivative of this function is always zero. So this means mass is conserved. Another property is that if we multiply again this equation with v and integrate, we get that time derivative of this integral is also zero. Hence, this integral is equal to the integral of the initial data. So this is called conservation of momentum. Another conservation is a energy conservation. So if we multiply f with v squared and integrate, then time derivative of this is always zero, and hence we conclude that this integral equal to the integral of this initial data. So this properties comes from physics. So it means that in the first property means that number of particles are conserved. In the second one is their momentum is conserved, and energies are conserved. And another something unexpected feature of these equations is that there exists a Lyapunov functional. So if we consider this h as an integral of the f with a log, you can see there is a log appears here. And for these three equations, the Boltzmann, Landau, and BGK, if we have a nice smooth solution, one can formally check that time derivative of this functional is non-negative. Hence, this is decreasing, and so it's a Lyapunov functional.
Non-positive.
Yeah, non-positive, sorry, yeah. So this is some general properties. This log somehow very important in physics, in statistical physics. Some fun fact is that when you visit Vienna, you can see in Boltzmann's grave, you can see this formula as a log. It is written in his grave, and it's almost same thing, but it's written in a physics language.
K is a constant of Boltzmann, yeah?
Yes. It's a yeah. And for more information about this field, I can refer these classical books. For example, the first book by Landau, Lipschitz, and Pitaevsky, and another book is by Carlo Cecchignani. They include everything about this field and equations. This was some first part of my talk. In the second part, I want to consider a specific model which I recently considered. So it's a semiconductor Boltzmann equation. So first, let's define what is a semiconductor. Semiconductor is a solid material with electrical conductivity between a conductor and an insulator. It means that electricity flow happens in these materials, but this electricity flow is not fast and efficient like aluminum or copper, but we have electricity flow. And some examples, if you are aware from chemistry, silicons and germanium are semiconductors. This type things use it almost in our almost every modern electronics, and they use it to create components like transistors, diodes, microchips. As in this picture, they are semiconductor devices. So this is just some material, and we use this in electronics. So our goal is to study the electricity flow of the in these devices. So as I told you, if we connect these devices to electricity flow happens, but it is not so efficient like conductors, but it's a little bit slow. And again here, the electricity flow happens because of the movement of electrons and holes. And we want to study the time evolution of these particles. So as I told you before, we can write some ODEs to study this each individual particle. But again, we have a large number of particles, and again, we cannot study by using Newton's law and classical mechanics. So we can study this evolution of these particles in this kinetic point of view. So again, we consider the distribution function of these electrons or holes. So let f the function of t and xv denotes the distribution of these particles. So it means f is a probability of having a particle at time t with position x and velocity v. Now in this model, I assume this x varies in a torus, a d-dimensional torus, and velocity.
Here, cathode is on the left side and anode on the right side. So,
sorry.
In this picture, cathode in the left side and anode on the right side.
Okay. Yeah. So, yeah.
Yeah.
Oh, sorry.
No. Yes, it's okay.
Maybe there is some mistake. Yeah. Yeah. Yes, and
electrons are moving from left to right.
Yeah. Okay. Yeah. So, sorry, there was a mistake.
It's a very simple diode. Yeah, diode.
Yeah. It's like diode. Yeah. And so under some modeling assumptions, some modeling assumptions on these semiconductor devices, we can write an equation for this distribution function, and this equation has the following form. It's again has this transport part on the left hand side, and on the right we have operator q, which is again nonlinear, and an integral operator. We have initial value f0. It's again non-negative and integrable. And this equation is called semiconductor Boltzmann equation. It's again has a nonlinearity, same nonlinearity as the classical Boltzmann, but it differs little bit. In this equation, in this operator Q, we have functions. M appears here. M denotes the Maxwellian distribution. So it's called Gaussian distribution. Yeah? And here, so the function sigma, it depends on V and V prime. It's a given non-negative symmetric function. Symmetric means that this equality holds. If we change V and V prime, these values of the sigma equal to each other. It's this points.
Is it between 0 and 1? Yeah.
Sigma or no?
F. F.
Yes. Yeah. F. Yes. Also in this, you can see this in this model we have 1 minus F and 1 minus F with V
and
prime.
values of F are between 0 and 1.
Yes. So
because it's the density of probability.
Yes. These terms appears from physics. It's called Pauli exclusion principle, and the physically meaningful solution, as you said, it has to be between 0 and 1.
Mm-hmm.
And we look for such a solution.
Yeah, I see.
Yeah.
Yes.
But
I didn't pay attention to that.
Yeah.
Okay.
Yeah. But for the Boltzmann equation, we don't have such a bounds. We don't expect it can be. We don't have such a bounds for classical, but for this one, we have this because in this equation, we somehow mix, we also use some quantum mechanics, and there is some physicists, Pauli, added such terms to describe this semiconductor devices. Okay, again, this equation conserves the mass, so we can integrate this equation with respect to x and v, and using this expression of this operator q, one can check that the time derivative of this integral is 0. Hence, this integral of the f equal to the integral of the initial data for all time. So this is mass conservation. However, there are no other conservations like conservation of momentum and energy. We only have conservation of this mass. Okay, this existence of solution to this equation has been studied by several authors, but in this talk, I just want to mention the work of Lucas Neumann and Christian Schmeiser. They proved existence of the distributional solution. So they showed that if there exist positive constants, kappa minus, kappa plus, sigma minus, and sigma plus, such that this function sigma is bounded from below and above by positive constants. And if the initial data satisfies these bounds, so this is a kappa minus and kappa plus appears, and M is this Maxwellian distribution. It's given here. So if we have such a bounds on the initial data, these people showed that there exists a unique distributional solution, and the solution satisfies the same bounds as the initial data. So we have somehow maximum principle for this. And also this solution is global. And because this is bounds, in particular, we get that solution is also non-negative and it's less than 1 because of this inequality. I am not going to give you the proof, but I can refer this paper. It proves this result.
They consider the periodic structure, crystal.
Yes, crystal. Yeah. So X in torus,
okay.
So existence is now well known. One can also consider the stationary equation. There exists the explicit solution to this stationary equation. So let's consider this equation, f infinity. It's given by this expression. M is again this Maxwellian. And kappa infinity is a non-negative constant. It's chosen so that the mass of this initial data equal to the mass of this f infinity. Since f infinity does not depend on x, it's just this integral, we don't have x, so we have just the volume of the torus. So this
And
kappa,
as I understand, the problem is to prove that the limit when t tends to infinity,
yeah,
the solution tends to f infinity. Yeah.
yes, and this is I call it as a stationary solution, but it's also called equilibrium for this equation. And this equation solves this stationary equation. So it's
Something like a stabilization problem.
yeah. So it is a time-independent solution.
Yeah, it means when t tends to infinity, we hope that solution tends to this f infinity.
Yes. And yes, under this constraint, that is mass constraint, one can show actually this solution is unique, the unique stationary solution, actually. One can show it's actually unique. And
it doesn't depend on x because of that.
Yes.
Because of that, you just multiply by TD.
Yeah, it doesn't depend on x, and it's already zero, this part.
Yeah, you just multiply
you can also check that this value of the operator Q is also zero. We can make it more precise here. It's all of them zero.
Okay.
Yes, you can find many solutions, but this under this constraint on the initial data, so its mass has to be equal to the mass of the initial data. Then one can show it's actually unique. And yeah, and using this function f infinity, we can consider a functional which is called the relative entropy, which I introduced to you before. So we have again this expression. So it includes this logarithm as in this classical Boltzmann equation, but we have extra terms, 1 minus f here, because of these terms appearing in the collision.
Some modified entropy.
Yeah,
it looks like a little bit unusual. Yeah.
Yeah, because of
this additional term.
Yeah, additional terms. We have this. We have to modify it, and again.
Who introduced this entropy first?
Yeah, sorry?
This relative entropy.
Yeah, it's relative entropy. Yes, we can, for example, forget the terms f infinity.
But it was introduced by somebody not so many years ago.
Yeah, it was introduced before by physicists for this model. Yeah.
By physicists, yeah. Okay.
Yeah, it's well known, and
yeah, okay.
Yeah. So again,
f and 1 minus f, these are here symmetrical, yeah.
Yeah.
F and 1 minus f.
Yes.
Yeah.
Yeah, and yes, if we assume there exists, so as I told you, there exists a distributional solution, but yeah, it also holds. But we can assume for all of my computations, you can assume there exists a smooth solution. So if we have a smooth solution and we can take time derivative of this functional, and yes, since f solves this equation by using this expression, we can check that the time derivative of this h is non-positive. So h is decreasing. And yeah, using this property, one can conjecture that h decays to its minimum because it's decreasing, and yeah, one can expect this h decays to its minimum.
Yeah.
But h attains its minimum when f equal to f infinity.
This is conjecture.
Yeah, it's conjecture. So because h is non-negative and it's zero at f infinity.
Yeah, and how fast is very interesting.
Yeah,
Yeah.
And one
T in some power maybe, or
yeah,
logarithm T in some power.
yeah,
But
so
maybe exponentially,
yeah,
not exponentially.
yeah. We will see now. We will see in my
It
next
seems
slide.
like T in some power, yeah, in denominator. Yeah.
Yeah, we can at least from the decay of this H, we can expect that solution converges to this f infinity as time
Yeah.
goes to infinity.
Yeah.
Yeah, and the question is to prove or disprove this convergence. And if we can prove this convergence, the next question is how fast is convergence rate? Because explicit and constructive rates, convergence rates are important for applications. So we can, for example, use this H and use some compactness tools and show that somehow this F converges in some weak sense. But we are not interested in such a convergence results. We want to get explicit rates here. And this problem has been studied by several people. I now want to little bit explain them. To do that, I introduce this norm. So it's a weighted L2 norm. So weight is this Maxwellian. And I denote it by this M with this norm. And this convergence, this problem has been studied by Lucas Neumann and Christian Schmeiser. They showed that if the solution, the partial derivatives of the solution with respect to x is uniformly bounded in this norm for all multi-indexes whose absolute value less than some natural number n, then they showed that there exists a positive constant such that this estimate holds. So on the right-hand side of this estimate, you can see that if t goes to infinity, it converges to 0. Yeah, and so it means f converges to this f infinity as time goes to infinity, and the convergence rate is this algebraic, and it depends on n. So if n is large, we get faster convergence, but if n is not so large, it's slow. However, in this result of the Lucas Neumann and Christian Schmeiser, they require this assumption. So they ask that the solution, the partial derivatives of this solution with respect to x must be uniformly bounded in this norm. And one can ask, do we have such a solution? But it's they ask this condition, but they don't know if there exists such a solution. So it's somehow a priori result. So they first assume, let us assume that exists such a nice solution, then we have convergence.
Sorry, uniformly bounded with a constant which may depend on alpha, yeah?
Yeah, but it should not be depend on t.
Yeah, uniformly on t.
Yeah, uniformly on t.
Yeah. Not, but yes, they are going when alpha it goes.
Yeah, yeah. So alpha.
This regularity, it means this is this assumption about the boundaries. Yeah, regularity doesn't mean.
Yeah.
What does it mean? If solutions define above regularity, it means they must be bounded. But it's not. Till now, it's not known. Is it these solutions are existing or no?
Yeah, we don't know, but there can be such a solution for. So there is existence result, but the existence result doesn't have such a regularity conditions. In this, we have just bound. If we just ask bounds on the initial data, then we have just only distributional solution in L1.
Yeah, the F is understandable, but for all derivatives, yeah,
Yeah,
there
and
is.
one can expect if we ask very nice conditions on the initial data, if we ask it's regular and all partial derivatives are bounded, one can expect the existence of such a solution.
It's a
But
regularity because there is no such a point where the velocity became very
yeah,
high, maybe.
yeah, and we don't know existence of
We
such a
don't know,
solution.
yeah.
Yeah, but one can expect maybe it's true or not, but it's they prove it.
It depends on gas.
Yeah,
And
yeah,
if it is a neutron gas in uranium, maybe it's not correct.
yeah, yeah.
Yeah,
Yeah,
okay.
and another result is by Klimovich and Lucas Neumann again. So they did different assumption. So they ask, they say if let initial data, so for difference between initial data and this F infinity, so we consider the derivatives. Let's assume this norm is sufficiently small for sufficiently large multi-index. So
For all sufficiently large, or for some efficient.
so let's say alpha is bigger than say 10 or 100. Let's say
No, for all big alpha,
for
or for
all
all,
for
for
all
all, yeah.
for all
Ah.
alpha. So it's somehow
But it follows from that that it's is bounded from small alpha too, no? Is it possible to prove, I think,
yeah. So
using the theorem like Lagrange theorem?
uh,
If the derivative is bounded, the function cannot be very big, yeah? Or can?
yeah. But we are just asking this condition on the initial data only. Yeah.
Yes, initial.
Yeah. If initial data can be given, and we can ask such a condition. Yeah.
Yeah, it's just condition on initial data. Yeah,
Yeah.
no, it's okay. Yeah, it's okay.
Yeah, it's something like that. Initial data should be close
If
to
it's
the
sufficiently small, it's a local theory.
yeah. It's like the initial data has to be close to this
Yeah,
F
and
infinity.
there exists a lambda.
Yeah,
We
there
don't
exists.
know how big is lambda.
Yeah, they can compute it explicitly depending on the size of this norm
Lambda
of
depends on this norm, maybe.
this norm. Yeah.
Yeah,
So there exist constants and lambda, and we have this bound.
yeah.
Since lambda is positive, this right-hand side goes to zero. So we conclude that the solution converges to this F infinity exponentially. Yeah.
There is no assumption about the regularity.
No,
No.
because
Only about the initial data.
yeah, okay. They also under this smallness assumptions, they also constructed a smooth solution, so the same regularity.
Yeah.
Yeah.
But it's
question?
not necessary to suppose that all the derivatives are bounded.
Yeah, they don't have to be bounded.
Yeah,
Can I ask
okay.
question, Dr. Tarjan?
Yeah.
Well, if F0 is equal to, so initial data is equal to F infinity, then what will happen?
Then solution is it's F infinity at all.
Раз эта функция удовлетворяет уравнению, то она и будет одна и та же все время, при всех t.
Одна и та же, да?
То есть там будет везде ноль. И, ну, в общем, в самом нижней оценке ft минус f бесконечность будет ноль просто. Ну, мне так кажется, я не знаю, is it correct or not? If f0 equals to f infinity, then the solution equals to f infinity, yeah?
Yes, because it's
Да.
stationary
There is
solution.
a theorem of uniqueness.
Yes, there is uniqueness.
Если у вас f бесконечность есть решение, и начальные данные, не зависящие от t, и начальные данные совпадут с этим решением, то они и дальше будут совпадать. Это будет решение, других нет в силу теоремы единственности.
Yeah.
И сходимость есть, да,
Yeah,
с любой скоростью.
Yeah, because F infinity solves this stationary solution. It's a solution.
Is there another a solution which doesn't depend on t. Only this one, or maybe some solution which depends on x. Maybe it doesn't depend on x. Is it possible to find the stable solution which doesn't depend on t but depend on x? Or no, only one. It's very strange. Maybe there are a lot of stable solutions. Stable, it means which they do not depend on t, or only one. It's a non-linear equation. It's very strange.
Yeah. Okay, so there exist infinitely many solutions. You can just consider this one, this expression.
Yeah.
So,
this is strange because
okay. So just example. So let's say k can be any function depending. No. So k can be any constant. Take any constant. It solves this. Yeah.
And why the solution tends just to this f infinity, but not to another n infinity? It's understandable in the last theorem because the initial data is very close to them. And it means that they
what is the very close? So it says, what is the very close? What does it mean? Sufficiently small.
Значит, существует такое дельта больше нуля, что если вот эта вот норма меньше дельта,
но вот эта константа, она должна зависеть от
дельта. Значит, формулировка такая. Я думаю,
должна зависеть от
существует такое дельта малое больше нуля, что если dxv альфа минус f0 минус f бесконечно с нормой меньше дельта, то тогда существует константа c, зависящая от дельты, и лямбда, зависящая от дельты, что верна эта оценка.
Да. Все это зависит от sufficiently small, да.
Да, и вы не можете указать этот дельта, поэтому sufficiently small. Если вы указали, то конкретно было бы. По-видимому. Но я не знаю, я не автор этой теоремы, но теорема намного лучше, чем предыдущие, потому что там вообще непонятно. Условия на решение до бесконечности накладывается. Это непроверяемые условия. А последняя теорема, она проверяемая. Какой вы берете начальные данные?
Да.
Нойман заменился автора и получил более сильный результат. Сейчас.
So I can sorry, my presentation, I can make it more explicit. So let's say this norm is bounded by some epsilon, and epsilon is sufficiently small. Then we can find constants, this s and lambda, depending on epsilon.
Ну да.
Примерно
как я сказал, что я ошибся, вместо дельта надо было эпсилон сказать.
Yeah. And so again, this has to be small for every alpha, so with whose absolute value is sufficiently large.
Вот это условие сильное. Альфа до бесконечности идут, видите?
It should be, alpha should be very large.
Да. Это очень сильное условие.
Yeah. But in practice, it is not a priori, because you can find such an initial data, yeah? You can find many initial data which satisfies this.
It's possible to find this F0.
Yes, F0, yeah.
Okay.
And
alpha also, right?
Нет, альфа любое. Вот в этом
No. So let me make it precise. So alpha.
No, sufficiently large. Sufficiently large. It's also not any, but sufficiently large.
Нет, здесь sufficient. Значит, начиная с некоторого большого номера, для любого альфа больше этого.
Не так. Для какое-то большое число.
Only one alpha.
Only one alpha. The alpha does not depend. So the absolute value of the alpha is given.
It was not necessary to say sufficient. There exists alpha.
Yeah.
So if there exists alpha, so that this norm is less than delta, for this alpha, or for all alpha which are sufficiently large.
No. So there exists a fixed alpha. The absolute value can be, say, 10. We fix 10, and we fix epsilon for every so alpha and
what does it mean for every alpha? For every alpha greater than 10.
So any alpha whose absolute value larger than, say, 10, for example.
For any alpha.
For any alpha.
Но видите, не для одного альфа это.
Не, по-моему, один.
No.
Модуль
Alpha,
больше единицы, один, там найдете все.
no, you can take alpha, you can take all alpha whose absolute value equal to 10.
Equals to 10.
10. Because you can take higher, but you don't need to take higher values, yeah?
It means that there exists such a number k for all alpha which modulus equals to k, да?
Yeah.
Not necessary to consider the alpha which are greater than 10.
Yeah.
Ну тогда да.
Yeah.
Теорему, в общем-то, физики, наверное, написать. Вот математически более аккуратно можно.
Yeah. So,
Ну теперь понятно, что тогда действительно можно F0 найти может. А если вот так вот для любого, тогда такого F0 может и не найтись.
Они должны совпасть тогда.
Yeah. We just improve these results. Don't worry so much because
now you can explain us your own results. Yeah.
Yeah, my own results. So
it's okay because it's 47 minutes. Yeah.
Yeah. So
it's previous works.
Yeah. It's previous works, and we want to improve these results.
Yeah. Okay.
And in my recent joint work with Marlies Pirna in Germany, we managed to prove this theorem. So we ask same assumptions as in the existence result. So we ask this sigma is bounded from below and above by constants, and we assume same bounds on the initial data. Then there exist explicitly computable constants, lambda and c. This lambda and c depends on this kappa minus, kappa plus, and sigma minus, sigma plus, such that this estimate holds.
Please, can you show the previous result, the previous slide?
Yeah.
Yeah.
So
okay.
We somehow removed these assumptions on
next your result.
Yeah.
It's excellent. Yeah.
Yeah.
There is no assumption about the derivatives.
Yeah, we somehow removed this assumption.
F0 minus F infinity must be have any value there. It doesn't matter.
Yeah.
But exponentially exponentially tends to F infinity solution.
This is recently published in this journal, Journal of Differential Equations. And this results, as I told you, improves this previous results. And our idea of the proof is that we construct a suitable Lyapunov functional by modifying this the relative entropy. Our ideas are somehow based on two methods in this field of kinetic theory. So there are two methods called entropy dissipation method, which was developed by Desfilates and Villani. And there is another method, it's called L2 hypercoercivity method. It's developed by these people, Dolbu, Moho, and Schmeiser. So we have learned these two methods and combined them. And by combining them, we constructed some nice Lyapunov functional so that we can get this result. So
for any initial data, we should satisfy this upper double inequalities. Yeah. You can prove this stabilization. Yeah. It tends to F infinity.
Yeah.
Okay.
Somehow in this result, somehow these people somehow try to use this method, entropy dissipation.
Fair enough.
Somehow you may not be aware, but we have somehow combined some another method, and by combining that we managed to construct some nice Lyapunov functional. Certainly also
from Münster University too?
Yes.
Yeah.
So I can show you how we construct a Lyapunov functional. So let me denote by this J, which is a function of t and x. It's an integral of this difference, and I multiply by v, and I this f minus f infinity, and just integrate with respect to v. So it's a vector. and let phi be the solution of the Poisson equation. So this is a Poisson equation, but on the right-hand side, we have integral of this difference with respect to v. And we look for phi, whose integral is 0 with respect to x. And it's elementary to show that there exists a unique solution to this Poisson equation. Yeah? And using this J and phi and the entropy, this relative entropy, we consider following form of the functional. So it's sum of this entropy, which is given here, and the term which appears, which includes this gradient of the phi, which is the solution of this Poisson equation, and this G, which is a vector given by this one. And delta is some non-negative constant. We will fix it later. So idea is to prove this differential inequality. So to show there exists some positive lambda such that this differential inequality holds for all t. If we have such a differential inequality, Grunwald's inequality implies that this functional decays exponentially. Yeah.
Yeah.
Because it's just integrating this, it's called
Yes.
Grunwald, and we can conclude this exponential decay of C. So our goal is to show this functional satisfies such an inequality, differential inequality.
So the problem was to find this Lyapunov equation, Lyapunov function.
Yeah, this is hard. But it's obvious that entropy is decreasing, and it's natural to consider it. Yeah. But we add some extra terms. We somehow modify a little bit the entropy.
You need to choose delta 2, yeah?
Yeah, we choose delta, some constant, which is it will be small constant, but it
if
does
delta
not.
is small enough, then you have this inequality, and use the Grunwald inequality.
Yeah, its idea is very simple, but the problem is construction of this.
Yes,
functional.
idea may be simple, but to find the phi, to this and to find this E of F, E capital.
E capital satisfying this inequality is big problem.
This try and error, I think, a lot of.
Yes.
Yeah, okay.
Yeah, so we consider this functional. So first, so again, I use this notation. So with M, the norm, this vector norm is this weighted L2 norm.
The same,
the same. And so we can show that if for this functional, if delta appearing here is if it's small, we can show that this E is we have this inequality. It means that E is equivalent to this norm somehow. Because E can be bounded from below and above by this norm, by some constants. And it's very simple. So I just give you some details how one can prove this. So we first consider this part. So we can just use this Holder inequality. So we can bound it by L2 norm of phi and j. But in the definition of the phi and j, so you can see that j depends on this f minus f infinity. And also this phi depends on this, again, difference, f minus f infinity. But we have integrals. But however, using this, we can bound that this L2 norm of the phi and g can be bounded by this norm. But we have square because we bound all of them. So this can be proven. I don't want to give details, but you can expect using this appearance of this f minus f infinity in the definition of g and phi. Okay, we have this estimate. Then let's consider this part, this entropy part, f log. Let's denote it by s. So it is, we can consider s is a function of f. So its value when f equal to f infinity, it's equal to 0. Also, if you compute its derivative with respect to f, its value at infinity, it's also 0. Also, it's a second order derivative given by this expression. And since these values of the S and its derivatives are 0 at infinity, we can use the simple mean value theorem. It says that there exists some G, which is a combination of F and F infinity. Sigma is some number. It can depend on T and X and V, but we can write such a we have this equality because of just mean value theorem.
The main problem is to find such a theta, yeah?
Yeah, but you can assume theta is so we don't want to find the explicit value of this theta, but it's important.
You just compared theta 0 and theta 1, and between them there exists theta.
Yeah, what is needed is we just need it's between 0 and 1.
Yeah.
But by the existence theorem, F satisfies such a bound, for all time and for X and V. Hence, we can also conclude that same bound can be written for G, because it's a combination of F and F infinity. Yeah? Hence, using this bound, so we have the same bound for G. We can find some positive constants, such that this product, which appears here, 2G, 1 minus G, can be bounded from below and above by some constants and this M, the Maxwellian. So, this estimate, we get this estimate from these bounds. And hence this, we can estimate this S with this 1, and S appears here. So we need to take integral. If we take integral, it's equal to this norm. Hence, by combining the first estimate and this last estimate, we can get such an estimate. So C2, which appears here. So this norm, but we also have such this one, C1, but we also have a delta here. Therefore, we have C1 and delta and this norm. We have also similar bound from above. And hence, if delta is sufficiently small, this constant is positive. Yeah, it will be positive. So this lemma can be proven by this using these arguments. Yeah. And another. So we know this functional is equivalent to this weighted L2 norm. Next, we now consider the relative entropy. So as I told you before, the time derivative of the relative entropy is non-positive, but we can compute it explicitly. When you compute, we get such an expression. Here, in this expression, M is a M. We have M and M prime. M prime is just instead of V, we put V prime, and F prime is also defined similarly. Here, capital F denotes this quotient, and also this F prime also this denotes the same quotient with F prime. We have this explicit computation for the time derivative, since this is a convex function. So log this, if we multiply this, it's always this product is non-negative. Hence, the time derivative of this H is non-positive. So let's denote this integral by df. And we have just this expression. This is just computation. And there is some observation. So let's define some nonlinear projection operator. So P projects F to this function, which has this form, where this again, M is Maxwellian. Kappa is a function of T and X. It's chosen so that the integral of this function with respect to V equal to the integral of the F. It is operator defined by this condition. So it's just somehow projection operator. So it's maps. We call it projection, but you can consider it as just an operator. And an observation is that this D, which is equal to this integral, vanishes for such in such a functions. And so this somehow makes 0 to this right-hand side of this time derivative of h. And using this fact, we proved this inequality. So we can estimate this this part on the left-hand side by this integral, but including this projection, because this appears because of this d is 0 when we put the projection on the. So instead of f, we put this pf, then it's 0. So using this, we can estimate the time derivative of h, and it's very crucial. And also the second term, which appears in this functional, so delta times this part, we can estimate similarly. So again, with using this p, the projection operator, with these terms. And since this functional e is sum of this entropy and this term, using this estimates for this estimate and this estimate, we can get this estimate for the time derivative of this e. Again, we have a delta. If delta is small, this constant is positive. Again, so we have two terms, this f minus pf and pf minus f infinity. If this constant's positive, we can use Holder inequality to these functions, because if we use Holder inequalities, pf can be cancelled, and we can get f minus f infinity. So by using this Holder inequality and assuming delta is small, we get this bound for the time derivative of this e. By definition, it's equal to this norm. But however, in my lemma before, I showed this functional equivalent to this weighted L2 norm. Hence, in this estimate, I can replace this norm with e, this function e, but with different constant here. Hence, I get that there exists some positive constant that says this time derivative of this e satisfies this differential inequality, and I conclude that this by Gronwall inequality, this functional decays exponentially. Also, in my lemma, I showed this e is equivalent to this norm, L2 norm. Hence, I can also use, and with some different constants, I can conclude the same estimate for the L2 norm. Hence, this proves our main result. So this estimate in our result is equivalent to this estimate because of this e equivalent to these norms, and hence this proves our result. It was just some ideas, but I used some inequalities, but they are not obvious, but they are just ideas. And there are some literature. So this is a book about these semiconductor equations. There are some works I mentioned before. And thank you for your attention.
Thank you very much. Any questions? Вопросы есть, может быть?
А вот у меня последняя лемма. Там непонятно, что имеется в виду. И слева, и справа одна и та же норма. Там стоит...
Это эквивалентность.
Эквивалентность.
Просто.
This one, yeah.
Вот это вот, да.
Слева и справа одна и та же норма. Ее можно убрать вообще.
Не, что энтропия эквивалентна вот этой норме, я так понял.
Да.
Да, и если оценивать энтропию сверху-снизу, достаточно оценить вот эти нормы сверху-снизу, это будет то же самое, да, наверное. Но это именно для стабилизации, наверное, нужно. Так, Гайрат, что вы скажете? What's your answer? The question was why you need this double inequality. Is it?
Yeah, because yes. So I want to prove this one, but first of all, I am constructing this functional, and I want to prove such a decay for this e. but uh, but it looks complicated, yeah, and it's not obvious if it is really measures between distance f and between f infinity.
Yeah, I see. You need to prove this inequality for the derivative, and because of that, you need this
also
double inequality.
So also this equivalence of this E helps lets me to replace this inequality with this exponential decay for this L2 norm. And L2
Здесь,
norm
по-видимому, так, слева заменится по одному неравенству, а справа заменится по другому неравенству. Rahama, chapter first. No, you need to estimate from the below using one inequality, and the right-hand side from the upper estimate using another inequality. По-видимому, конечно, вы правы, совершенно верно, Анатолий. Используются они будут при разных t. А еще раз, я на кого-то отвечаю. Да, по-видимому, так вот f будет при t равном нулю оцениваться правая часть, а при t произвольном будет использоваться левая часть.
А так просто не
А так да, но они будут использоваться в разных случаях. И тогда получается вот это можно применить неравенство Гроновой, насколько я понял. Вот, можно будет использовать неравенство Гроновой, да. А вот внизу даже вот написано уже. Вот. Еще раз, да. Так, еще вопросы, может быть, или какие-то комментарии? Пожалуйста, Равшан Ражевич.
Can you show me this last theorem from which you started to do it? Just for the other authors, the last one.
Yeah, it's I am just stating my result again.
No, last result before this.
Okay, the authors.
This Neumann. Well, looking at this result, how did you come to the idea that this result can be improved, or there was some hypothesis?
So we so somehow we so as I told you, my proof based on some methods. So for linear equations, if we have a linear equations, we can nowadays. So in recent 20 years, many now this long-time behavior of this kind of equations is now very active research, and new methods has been developed. But they all of them are only for linear equations. They works well, but for nonlinear equations, one has to require such conditions. We somehow try to improve this. To replace this this smallness assumption or a priori uniform bounds, we somehow a little bit learned some new methods, and we used these bounds on the solution. They are very important.
Yeah, this bounded is natural because it was appear in previous works also.
So this bound is somehow
quite natural.
It's natural, but one can also find a solution which may not be satisfy these conditions. But it's a moment we managed to prove this under this assumption. But a very important thing is these bounds are very important.
Maybe this double estimate is very important because, видите, Рожан же, такое ощущение, что предельных решений может быть много. И какое начальное возьмете, оно к такому предельному и будет стремиться. Вот здесь указан интервал для начальных. Вот с этими начальными решение предел пойдет вот к тому и бесконечность. Но если возьмете, может быть, другие начальные данные, оно, может быть, пойдет к другому предельному. Тут же не ясно. Если предельно, то есть, короче говоря, если решений, не зависящих от t, много, то ясно, что и все начальные данные разбиваются на классы, в каждый из которых стремится к своему. Вот. Здесь, видите, если это начальное не очень отличается, так сказать, вот, от этих вот величин, то, скорее всего, это гипотеза, надо смотреть подробно, как вообще надо знать физику здесь, это трудно. Это же нейтральный, там было сказано плазма, но это на самом деле нейтральный газ. Здесь механические столкновения идут. Упругие столкновения, то есть как бильярд было сказано. Сохраняется закон сохранения импульса при таком столкновении. Вот, и только. И поэтому... Нет, ну, в общем, I think that this result is very interesting, and comparing with previous results, you have a very big success. Thank you very much for your very interesting presentation. Вот. Мне кажется, было интересно, нет?
Да, конечно.
Вот, ну, я смотрю сейчас, последние доклады в основном посвящены нелинейным задачам. Но, наверное, наступило время нелинейных задач, так, наверное, да. То есть они всегда были, но сейчас интерес к ним возрастает. Потому что линейные уже там, в линейных уже даже, знаете, тесно стало, по-моему, нет? Как вы думаете, Арсений Владимирович, слишком много людей занимается линейными задачами?
Да, ну, среди линейных задач тоже есть те, которые...
Конечно, есть линейные задачи до сих пор очень трудные. Вот этот $1 миллион обещали за одну нелинейную задачу. Вот она всех туда, значит, перетянула, всех математиков туда. Да, но бывает такое, да. Кто не хочет получить $1 миллион? Если доллар обесценится, допустим, инфляция, то тогда, возможно, интерес к этой задаче пропадет. Да. Тем более, что обобщенное решение там существует, и численные тоже существуют. Здесь уже чисто спортивный интерес получается. Уже именно гладкие найти, так сказать, да. Так, ну ладно, я отвлекся. Я думаю, надо поблагодарить докладчика, да, за интересный доклад. Thank you very much for your very interesting report. And we wish you new successes.
Thank you.
Да, всем большое спасибо.